get to this point in space and time, she had to be residing somewhere in this cone. Doesn't mean you can choose to go back. You'd have to go backwards in time to do that.
But if time isn't there anymore, or it's flip-flopped in the horizon, would it,
Right.
wouldn't it be not holding her in linear time anymore?
Yeah, let me think about that for a second. I'm going to show you an animation I think will answer your question. Isn't this weird? But it's fantastically powerful because if you go look at Kip Thorne's book that he wrote that looks like a telephone book and try to get this insight from the math, you're going to spend a lifetime doing that. This allows us to actually make some progress without doing math. Now, see the red lines? I'm just emphasizing here, the red lines focus on the idea that if you're at this place and time, and you haven't crossed the horizon, your entire future is confined to this, between these two red lines. And you can choose, if you want, to cross the horizon. Or you could make a little effort with your rockets and stay out and just observe the black hole from a distance. If you go there, you're going to die. And I'll show you some specifics about what that means. Okay, so now, the same drawing, I'm just reminding you here that Alice and Bob can send signals to one another using light beams, and the light beams travel at 45-degree angles. So here, right here, I don't know if you noticed that, let me redo it. Here's Alice and Bob. They are not at the same place, but each of them is on their own trajectory. Alice is a little closer to the black hole. She's following this trajectory. And here's Bob, and he's following this trajectory. And she sends him a signal. There it is. This little blue thing. And then he sends her a response, which she gets sometime in the future. Remember, time is like a windshield wiper blade. So long in the past here, and now she gets this signal on this line, which is in the past, but not so far back. And then she responds to him, and he responds to her, and so forth. Right? So there is the equivalent of this set of communications. She says, "Happy birthday." He says, "Thank you." She said, "I'm going to send you a gift." He says, "I hope it's expensive." So, but the light rays bounce around and they're distorted because of the shape of this crustal diagram. Now, here's the animation that I mentioned when I was talking to Katrina about how time progresses. Once again, here's the horizon, and this line doesn't have the dragon teeth, but that line is the singularity. The spatial coordinate changes to a time coordinate. I'm sorry, it's jittering. I hope nobody has a problem with that. But you see what happens here? The computer is not digesting this well, but you see what's going on. This is different positions. Like the curve that's here is a place. This one's a little closer. The curve here is a little closer, and the one here is a little closer, and so forth. But notice, when they cross the horizon, they start going that way. And you can't go backwards in time. So once Alice is in here, it looks like we killed it. Once Alice is in here, her future is a place, and we call that place the singularity. She has no options once she's inside the horizon.
So she stays just as she is forever?
If she is, I will show you examples in a second, if she decides to cross the horizon, now she's inside here, she will encounter the singularity, which is certain death.
And then but she never ages.
We'll talk about that. It depends on who the.
There's the plus.
Yeah. That's true. I hadn't thought, that's a good way to. All right, so the spatial and time coordinates switch, which is a little bit shocking. Inside the horizon, your future is not a time, it's a place. And that place is the certain death of the singularity. So now, here's our Alice and Bob. And it's convenient to just treat this as if one of them's closer to the horizon. Here's the singularity, here's the horizon. We could say Alice is a little closer, and to avoid falling in, she's got a rocket that keeps her levitating. The same thing applies if you're in orbit, but it's just simpler to do it this way. She's got a little rocket, and she's staying levitated. And here's Bob. He's a little timid, so he's a little farther away where it's safer. If they shut off their rocket, the gravity will draw them in. And I've chosen to do this, what we call radial motion. That all the motion I'm going to show you in subsequent slides is all about motion this way. The same thing applies if you're in orbit. It just makes it more complicated to draw it. So, once again, here's the Kruskal diagram. There's Alice and Bob. And they're not moving. Remember, if you stay on this line, you're not moving, but time carries you along. And they're going to communicate by light beams, and they're staying levitated so they don't fall in the black hole. But Alice is going to shut off her rocket, and she's going to explore the black hole. And so we're going to answer these questions. What does Bob see when Alice approaches and crosses the horizon? What observation does he make about her, what's happening to her? What is actually happening to her?
He's in the same time, place.
What's that?
He sees the same time, place as
We shall see. We shall see. Can Alice send signals to Bob? And if so, for how long? And what is her future? So remember, if you're on one of these lines, come on, mouse. If you're on one of these lines, you're not physically moving. You're just, on the map, you appear to move only because time is advancing. Now, we have a little thing we have to deal with at the bottom of the screen. This experiment makes simplicity out of real life around a black hole. Black holes, not all of them, but many of them, are surrounded by accretion disk of gas and dust and stars and everything that's going to eventually fall into the black hole. And that stuff is rubbing against it's all rubbing against each other, and is enormously hot, dangerous, radioactive place. It's not this simple. But it's a thought experiment to imagine an isolated black hole that doesn't have an accretion disk, but it has some other issues for our astronauts. And they're called tidal forces. I'm going to show you a drawing. All right, so here's an astronaut hovering above Earth. And the astronaut is falling, and if they have sensitive instrumentation, they would notice that not all of them is falling in the same way. And what we mean by that is every part of this astronaut's body is falling towards the center of the planet. So along his center line, everything is falling towards the center, but his right hand, this one, is not falling in parallel to this. His right hand and all the atoms in it are falling toward the center of the planet. So this, and his left hand experiences this. So if we watch him from the outside, we see different parts of his body are feeling different influences of gravity, because all this stuff is falling toward the center of the planet. In his frame, inside his little capsule, he experiences this. He feels a force toward the center of his body. In fact, it was easy to do. Imagine I'm the astronaut, I've got two apples. Everything in the capsule is falling toward the center of Earth. If I let go of the apples, this apple is going that way, towards the center. And this one's going that way. So over a period of time, the two apples are going to approach one another. And they will meet when you get to the center of Earth. Does everybody following that? So everything is, this is called a tidal force. For Earth, real astronauts floating around Earth, this is inconsequential, too small to measure, but near a black hole, it's a big deal. And the smaller the black hole, the stronger the tidal forces. A solar mass black hole has enormous tidal forces. That's why I said if there's a solar mass, earlier I might have said Earth-sized solar black hole. That's not what I meant. A solar mass size black hole is like the size of a baseball or a softball. The tidal forces are stupendously huge because it's a tiny object and everything is falling toward its center. So that's a factor in how comfortable you are traveling near a black hole. And here's what happens. Oh, there's another factor too. I forgot to mention, because the astronaut's feet are closer to the object, there's more gravitational force at his feet than at his head. So we get a technical term out of this called spaghettification. Remember I said that if you have two apples and you let them go, as you approach the object, the two apples are going to move together because everything's on a trajectory toward the center. But your feet feel more acceleration than your head, so you get stretched this way and compressed this way, and that's what this cartoon shows. Spaghettification. And I've taken a little time to do some calculation, which I'll show you here. And what this shows you is how long you can survive. We'll get back to the crustal diagram in a second, but I just wanted to make this realistic. The black hole at the center of our galaxy has a mass of 6 million solar masses. That's what this little symbol means. And the time, once you cross the horizon of this black hole, the time before you hit the singularity is 60 seconds. So you have a minute to observe what's going on inside the black hole. Now, once again, I want to emphasize a real black hole is surrounded by so much chaos and debris, you would be unconscious long before you got to the horizon, but we'll set that aside. This is called a Gedanken experiment, something that Einstein was famous for. It means a thinking experiment in German. And you think up these problems and you try to work them out without having to actually go to a black hole and be killed. Now, the question is, what is your survival time? How strong is the tissue in your body so that you survive the tidal forces of crushing and stretching? And for a galactic-sized black hole, like the one at the center of our galaxy, you have 9 seconds once you cross the horizon, and then you cease to be alive. A supermassive black hole, this is 21 billion solar masses, and there is one of those out there. The time to travel from the horizon to the singularity, about 3 days, and you would survive 13 hours. The bigger black holes are less dangerous. You can survive longer. This is the imagining that you're spaghettified. Okay. Back to Kruskal. So, before doing the experiments, oh, question, yes, sir.
Yeah, wouldn't some of those same effects be present on, before you cross the horizon?
Yes, they most certainly are. There is tidal force, but the tidal forces, except for the small black holes, the tidal forces are benign until you get close to the horizon. And we're dealing here with our example can be the black hole at the center of our galaxy, 4 million solar masses. You'd be okay until you got to within the horizon, which is, I should have done the calculation. The horizon of the black hole at the center of our galaxy is probably something like the size of our solar system. If you're like 3 times farther than that, you would be okay, you'd be comfortable. Once you get close to the horizon, things start changing. So we're back to the Kruskal diagram. And I'm gonna show you communications between Alice and Bob. So there's Alice in the past. Remember, once again, this dotted line, because this is past infinity, this solid line. This dotted line shows sometime long in the past, Alice is going to send a message to Bob. You know what I should do? Maybe after the break, I will have a clicker where I can walk around. So she sends a message to Bob, and then she sends another message to Bob. I'm only showing one of his responses, otherwise the drawing gets too cluttered. But imagine, he's responding to her every time she sends a message. Remember, neither one of them is moving. They are peering in different places because time is advancing. Still, nobody's moved. But she's sending him signals. There's the one response, this blue line, shows he does respond to her. He's being polite. And now, and so this yellow says what I just said. Alice and Bob have not moved. They're using their rockets to stay in place. So let's look in more detail. Now, Alice, in this case, is going to cross the horizon. And she, ahead of time, they have a meeting. And she says, I will send you a signal every second. I'm going to say, beep, beep, beep. It's a kind of clock. Every second, she sends him a little notification. All is good. All is good. All is good. So she's sending him signals. Right here, she decides to shut off her rocket, and now the gravity of the black hole is going to take over and drag her through the horizon. And she continues to send him signals. Now, I want you to notice something very important. I put some times on here. This is 500 seconds before she is going to shut off her rocket. She sends signals. Here's 10 seconds before she shuts off her rocket. Right here, at around, let's see, this is, I don't know, -5 seconds, she shuts off her rocket. She's still sending him signals. But this one, notice, when does he get that signal? At t = 500. Far in the future. That is, she sends a signal, but because of the geometry around the black hole, it takes a long time for that signal to get to him. So early on, she sends a signal, he gets it at the appropriate time, which is dictated by how far they are apart when they start the experiment. But because this is so crazy nonlinear, notice, this is 500 seconds in the future, then it's 5 million, and then there's infinitely far in the future. Yes, sir?
Well, it appears that she won't receive his response until she's already sent another signal, correct?
Yeah.
Everything's getting crazy now. Okay, so she sends, see the yellow signal that she sends? I just put up there? Let's put it up again. He's not going to get that for a long, long time, many, many, many years in the future. Because she's in a location where space-time is so distorted that the signals she sends are struggling to get out of the gravitational influence of the black hole. Now, it's not, and let me make something very, very clear. It's not because her signals are going slower. It's because the time between them appears to be longer. That every signal she sends is moving at the speed of light. I'll refer you back to weeks and weeks ago. I told you everyone measures the speed of light the same way. It's always the same number. So it's not because her signals are propagating slower, it's because it appears that her clock is slowing down. She agreed ahead of time, I'm going to send you a signal every second. But because of the curvature of space-time, Bob says, wow, when we started this experiment, there was like 1 second between signals. And now it's more like minutes, and now it's more like years, and now it's more like hundreds of years. Her clock is slowing down. That's his observation. We're going to have a break here, but let's finish this slide. as she gets closer to the hole, remember, once she leaves this curved trajectory, she is now, if she didn't move, she'd be on this curved trajectory. But she's agreed, right at this point, she said, I'm gonna drift in. So she's going this way, she's gonna cross the horizon. She sends this signal, it could take millions of years for him to see that signal arrive. Yes?
But even if she doesn't move, the time for the signal to arrive still goes up, just because of the curves.
Oh, not true, not true. If she didn't move, she'd be on this curved trajectory.
Yeah.
But Bob would also be on this curved trajectory,
Oh,
right? So, well, let's go back. Be patient, Pam, we will have a break.
Oh, no.
Let me show everybody.
Blame me.
Well, because you're in charge.
You're in charge.
Let's go back to, I'm sorry, it takes a while. Remember this? This is where nobody's moving, and they're sending signals back and forth. The blue lines, she sends to him and he sends to her, and back and forth they go. If they didn't move, I know the arrows are different lengths, but that's an artifact of this map. This time, for her to send a signal from here to here, that time and this time are exactly the same. Just because of the distortion in the map. Just think about Greenland and Australia. So they're not moving on this chart. Boom, 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 boom. Nobody's moved. The arrows are longer simply because the map is crazy. Yes, sir.
If Bob can measure the speed of the message coming to him from its beginning to end, would it appear to him to accelerate?
No. There is something that does happen, which I'll explain after the break. But it's what you said, no, that's not what happens. So let's go back to where we were, and we'll have a break. Pam maybe has some announcements, and then this adventure will continue. I hope all of you are hanging in there. Remember, if you lose track of what we're doing, because there's so much graphic material here, hang on to the results, which is we learned about spaghettification, how long you could survive in the vicinity of black hole, how to graphically depict the horizon and the singularity. Okay, Pam, do you have something to say?
I do. On February 20th is the next Midday Morsels, and it is about fake news by Maggie Farley, and it's 11:45 to 12:45 at the First Universalist Church, which I thought it was at the Park Hill. Hold on a second. Yep, no, First Universalist. And then, Ollie is open on President's Day, Monday, February 17th. The only exception is the Central Cinema, which will not meet due to First Plymouth being closed. The spring catalog will be available on Monday, February 17th, and registration will begin at 12:01 a.m. that day. And we have Hear the Opera of Colorado Artists in Residence on March 3rd from 9:30 to 11:30 a.m. at Park Hill United Methodist Church. And I'm going to leave these over here if anybody wants to take a closer look at those. And that's about all.
Okay. So lots more to show you, so maybe we try to be, it's almost 10:40, we'll be back at 10:50, and we will resume.
So I have,
Sorry.
I have many books at home by Brian Green and Lauren and would be of any use for me to bring them in so people can take a look?
Yeah.
This is paper.
Now, I've shown
It's
that
about
if you get some
Yeah.
examples. You have Thorn,
Well, for example, I've got half of the books at home that showed up on your
Oh,
site.
But the thing that's throwing me the most
yeah,
is
just people on a foot
these
home
curves
and
are all
stuff
going
and
like this,
see
and the
what-
first one
Yeah,
is
yeah, I think that would be-
slingshotting around the singularity.
Corollary for announcement. Next
Right,
Thursday,
but the singularity,
There's
So the first one, so here's the singularity, he was showing how like bends, and if it's going like that,